Visualize it. I'll give it something to do. Coach, wherever we go. Visualize it. I'll give it something to do. Get a wildfire burning. Visualize it.
Hey, what's up, everybody? Welcome to another wonderful day of math class. This is Mr. Cartwright speaking, and it is day 3. We are chugging along, and we are making progress. So, to start off today, we are going to do more algebra review. Yeah! Super excited. So, starting off with systems of equations. Once again, we have a systems of equations here, and in any system, you can solve it however you want to. However, there is always going to be a way that's easier. And Mr. Cartwright's all about the easiest way possible. So, in this system, we have 3x plus 2y equals 10, and 6x plus 3y equals 7. I can see that 3x and 6x can cancel each other out, but they're not quite there yet. So what do I need to do? I need to make this 3x into something that will cancel the 6x out. I need to make it a negative 6x. So to do that, I multiply 3x by negative 2x. Or sorry, just by negative 2. If I multiply it by negative 2, I would now have negative 6x, right? So I need to multiply this whole top equation by negative 2. And I'm going to write this new equation right below, right? So negative 2 times 3x would be negative 6x. Negative 2 times positive 2y would be a negative 4y. And finally, negative 2 times 10 would be negative 20. Now we can see that these equations will cancel each other out. So 6x minus 6x would be 0x. 3y minus 4y would be negative y, or negative 1y. And 7 minus 20 would be negative 13. All right, we can see that the 0x doesn't matter. And negative y equals negative 13, y equals 13. We are still not done yet. We have to take this 13 number, and we have to plug it back into one of our original equations. I'm going to pick the second one because we haven't messed with it that much. So if I plug in a 13 for where the y is, I would be left with 6x plus 3 times 13 equals 7. 3 times 13 is 39. Still have 6x. And to get rid of the 39, I'm going to subtract it from both sides. 7 minus 39 is a negative 32. And 6x equals negative 32. Then we divide by 6. And we get x equals negative 32 over 6. Or 5 2/6. We could take 5 2/6 and plug it back in to find our y value. Or sorry, never mind. We already have our y value of negative 13, or positive 13. So our x value is negative 32/6, and our y value is positive 13. Systems, woo! Yay, you gotta love them. They're so much fun. The other way we do systems is substitution. So this was called addition, subtraction, or elimination. We use a bunch of different words for it. And this one is called substitution. What I want to do here is I want to isolate one of the variables. Get one thing all by itself so I can plug it into the other equation. This top guy looks kind of complicated, so I'm going to start with the bottom guy. The bottom guy is one step away from getting y all by itself. So to do that step, I would have to subtract 3 from both sides. I now have y, I'm going to move it over here. Y equals 2x minus 7. Subtracted the 3 from the 4 to get negative 7. Y equals 2x minus 7. Now, I can take that 2x minus 7, right? I can take this guy right here, and I can plug him in for where the y value is in the first equation, in the first equation. We do not want to plug them into the equation we just used because then we haven't really done anything and we'll get an answer that looks like 0 and it won't be correct. So we're going to plug in 2x minus 7 for where that y is. Writing the equation over here, we have 3x plus 4 times 2x minus 7. Now, once again, still equals 12. We have to distribute the 4 to both sides. I'm going to go ahead and rewrite this guy in a different color so you guys can see it a little bit better. So we had 3x plus 4 times 2x minus 7 equals 12. Cool. 4 times 2x is 8x. 4 times negative 7 is negative 28. And we have a positive 3x over here. That all will still equal 12. 3x plus 8x is 11x by combining like terms. Minus 28 equals 12. We add the 28 to both sides to get 11x equals 40. And when we divide both sides by 11, we get x equals 40 elevenths. And if it were an easier number, I'd plug it back in to find our y value. But we're going to go ahead and say that we could do that. Moving back to recursive equations. This is what we learned yesterday. Everything so far should have been reviewed except for recursive and explicit equations. So remember, in a recursive equation, you have to find the previous step to get to the next step, right? So if we have 1, what do we do from 1 to 4? What do we do from 4 to 16? And then finally from 16 to 64. Should be obvious, we multiply by 4 in each case, right? Times 4 times 4. Therefore, our recursive equation is pretty easy to write. It is f of n, let's make my marker a little bit, f of n equals 4 times whatever step you were on, because we multiplied by 4 to get to the next step. The recursive equation in this situation is pretty easy to write, right? 4 times n, we're done. Woohoo! All right, moving on to the explicit equation. The explicit equation is actually a lot harder for us to write in this case because it doesn't quite work and it involves exponents that we haven't talked about yet. So once again, we can still see the pattern is multiplying by 4 each time, right? But if we were to graph this, our x values are over here, our y values are over here. 0, 1 would be like right there. 1, 4 would be like right there. 2, 16 would be like right here. 3, 64 would be all the way off the page, right? So what we have is a parabola-shaped curve. This is not a line, right? It's not like our normal explicit equations that we're used to. So this one is actually an exponential equation, and you will learn a pattern for it later in the semester. But pretty much, you can solve it by creating your multiplication value as your base. So y equals 4 raised to the x power. This makes sense because if we plug in a 0 for x, 4 raised to the 0th power would be 1, and that's true. If we plug in a 1, 4 raised to the first power is 4, and that's true. And if we plug in a 2, we get 16, and a 3, we get 64. So this would be the explicit equation, although it's much harder to find than the recursive equation was to find. So recursive equations are actually a lot easier because all you have to do is know what's going on in between each step, and you're good to go. An explicit actually has to work for all the values that you plug in. Does that make sense? Please ask if you have any questions. And I wanted to talk real quickly about samurai swords. Samurai swords are the strongest medieval weapon ever created, and they are created by folding steel on itself. So they take a thin piece of steel and they bend it in half. And they stick it back in the fire, and then they bend it in half. So this is an analogy to pieces of paper, right? If you have one piece of paper, you can rip it up really easily, right? But if you have a giant stack or a phone book, it becomes much harder. Every single layer of paper multiplies the resistance by an exponential factor. So the way they make samurai swords so strong is by sticking them in the fire and then bending them back in on themselves. They do this to the point where they get over 20,000 folds, and that makes the samurai sword really, really strong. The same analogy can be applied to people, because when you are put through an adverse situation, when you are stuck in the fire, when you are forced to re-examine yourself, you become stronger. Your motivations, your willpower, your endurance, your intelligence, all of this is improved only when you're facing adversity. If you are just sitting on your couch playing video games, you're not growing, you're not becoming stronger. But thankfully, this situation has put you guys through some fire, and you guys are becoming stronger for it. And you have two situations. You can either become stronger or you can break. Those are the only two things that happen when you're put in the fire. Let's become stronger together, guys.